frequency. So next very important topic is breakdown in PN junction diode. So we are going to see how breakdown happens and what is the condition for breakdown. So you know that in forward bias there is no issues. The diode is conducting pakka and it is going to produce current. But in reverse bias, you have a very small amount of current called as reverse saturation current I naught, which flows actually due to minority carriers only. It will not flow due to majority carriers because majority carriers are not able to cross the depletion region because in reverse bias, the depletion region width is very large. As I told you already, if the bridge across the river is large, it will take larger time for crossing and you need more energy, right? Same condition here. This breakdown happens only in reverse bias because the majority carriers cannot cross. Only the minority carriers will produce a very small current called as reverse saturation current. But this current is ideally it is zero, but practically it will be in the order of microamperes or nanoamperes. Okay, so whenever you're going to increase the reverse bias voltage, slowly the reverse current will increase. Suddenly, when you're at one particular voltage, due to there's a sudden increase in the reverse current due to some sort of breakdown. So that voltage is called as breakdown voltage VBD. So at a particular voltage, suddenly the reverse bias current increases, which means the electrons, the majority carriers have acquired more energy to cross the depletion region. Okay, for that reason, that breakdown voltage, suddenly the thing is increasing. So once breakdown happens, the diode is again into on state. So diode is no longer blocking current and it starts conducting freely. And how you can control the current? Only by adding a resistance in the external circuit. Okay, only by adding resistance in the external circuit. So see here, forward bias, you know, it is after the cut-in voltage, it starts exponentially increasing. The breakdown due to avalanche effect in which thermally generated minority carriers cross the depletion region and acquire sufficient kinetic energy to produce new carriers. So when you have a particular voltage, these electrons will try to knock the covalent bonds and they will try to bring more electrons. One electron knocks one electron, it becomes two electrons go and knock two electrons, it becomes four. So it will multiply in powers of 2, 1, 2, 4, 8, 16, 32. It multiplies, and when more number of majority carriers are obtained, they will easily cross the depletion region, however large it may be, leading to what is called as breakdown. Okay. So avalanche effect is produced. So you have two types of breakdown in PN junction. One is called as avalanche breakdown and one is called as Zener breakdown. So at avalanche breakdown, the diode becomes not usable. Avalanche breakdown occurs with a very high value of voltage, and once avalanche breakdown happens, the diode will not be usable. Okay, diode, we cannot use the diode because at a very high voltage, diode will completely break down. But when you're asking about Zener breakdown, by heavily doping your PN junction diode without even disturbing the diode, I can produce a huge reverse bias current through a phenomenon called as Zener breakdown. So in Zener breakdown, the diode is not broken down. It is available. It is still working fine. But in avalanche breakdown, the diode will be completely broken down because it happens at a very high voltage. See, avalanche breakdown happens at close to 100 volt or 1000 volt, but Zener breakdown happens at 6 volt. So at 6 volt, the diode will not have any issues in functioning. At 6 volt, the diode reverse saturation current will be very high. And how do I achieve that? By using doping. So if I heavily dope my PN junction diode, then the reverse bias characteristics will have a breakdown, which will be similar to your forward bias characteristics. So in forward bias, after a cut-in voltage, the current is increasing exponentially, right? Same way in reverse bias, after the Zener breakdown voltage, the reverse current will also increase in an enormous way. So two breakdowns you have seen. One is avalanche breakdown. In normal PN junction diodes, we have this avalanche breakdown where one electron starts knocking other electron. So it happens as an avalanche of electrons. Avalanche is a group. So when a huge group of electrons are obtained, they will cross the depletion layer and they will go to the other side causing reverse saturation current. When you heavily dope your PN junction diode, the diode will never be called as PN junction diode. It will be called as Zener diode. So the diode becomes a Zener diode, and Zener diode has Zener breakdown. And Zener breakdown voltage is happening at a very low voltage of 6 volt. So where is 6 volt and where is 100 volt? You see, difference is both After crossing the breakdown voltage will result in enormous current. But in avalanche breakdown, after it reaches 100 volt, the diode becomes unusable. Diode தூக்கி dustbin போட வேண்டியதான் because it will burn out. But at Zener breakdown, the diode is still usable because 6 volt is not going to disturb the operations of my device. Okay, please understand these two types of breakdown, very, very important. Even in application point of view, you will be asked to explain the two types of breakdown happening in PN junction diode. Any doubts in this, you can ask. In breakdown, you can ask. I'll pause for a few seconds.
So,
Yes.
so for Zener breakdown to happen, the junction diode needs to be heavily doped, right?
Yes.
So once I achieve the Zener breakdown,
Mm.
if I keep increasing the voltage value, like when you keep turning the knob, right, it keeps on
Yes.
increasing. The current
Yes.
flow will keep on increasing. If I will it change? Will it ever change? Like, will it go past the Zener breakdown voltage even after that
No,
happens?
no. After breakdown happens, the diode will work like a constant voltage source. So the voltage across the diode will be constant.
Even if I keep increasing current flow through it,
Yes,
sir.
even if you increase the voltage from the RPS, whatever you are going to use in lab, if you connect a voltmeter across the diode, it will always stay at 6.
So, like,
Only the
first,
ammeter.
if it's 10 new ampere flowing through it and it's giving this breakdown voltage,
Yes,
sir, if
yes.
I increase the current flowing through it to like 100 new amps or something like that, it'll still be in the same breakdown voltage. It won't
See,
increase the voltage or anything.
as long as you vary the voltage from 0 to 6 volt, the current will be in microamperes. It will be slowly increasing in microamperes. Okay. Once when you cross 6 voltage, because of Zener breakdown, the current will be enormously increasing after that. It will become 100, 200, 300, 400, but your voltage remains constant as 6. It will not go beyond 6.
Okay, sir. But if it's not
Because,
doped, it will
yeah,
reach an avalanche breakdown and it'll
yes.
become like a normal conductor.
Yes, and can you guess why at 6 volt the breakdown happens in a Zener diode? What is the effect of doping? When you dope your PN junction diode, what will happen? When you
Uh,
heavily dope it, what will happen?
because the charge carriers increase,
The depletion region, actually, what is the size of depletion region? It will be almost 5 mm, right? Close to 5 mm in normal PN junction diode.
so it'll
When
be
you are going to
small.
heavily dope your PN junction diode, the depletion region itself becomes smaller.
It
So in the
becomes even
reverse
smaller.
bias, yeah, reverse bias, when I give 6 volt, the depletion layer size is not that much large for the carriers to cross. They will cross the depletion layer easily, which is giving rise to Zener breakdown.
Okay, sir. Thank you,
In
sir.
conventional PN junction diode, your depletion layer, the doping is very, very minimal. So the depletion layer region width is very, very large. The avalanche breakdown happens at larger voltage. But with same PN junction diode, if you heavily dope it, it becomes Zener diode. In Zener diode, the depletion region is just like a straight line. In forward bias, it is straight line. In reverse bias, it will be very, very few mm thick. So that the majority carriers can easily cross the junction, even at reverse bias condition also. So that is the reason why we are getting Zener breakdown at low voltage and avalanche breakdown at a very, very high voltage.
Okay, sir. Thank you, sir.
Okay. And the avalanche multiplication factor is given. I told you avalanche of electrons is produced because of this increasing the reverse bias voltage, right? So this is the avalanche multiplication formula. So M is going to be the avalanche multiplication factor. So 1 by 1 minus V by Vbd, the whole power n. V is the applied reverse bias voltage and Vbd is the breakdown voltage. And after breakdown, you can find this M value will be increasing exponentially. It will be very, very large. And N, we have seen N is again a device constant. It is 4 for N type. N type silicon it is 4 and for P type silicon it is going to be 2. So once you cross your VBD, when V by VBD value is going to be, the ratio is going to be larger, then I think the multiplication of three carriers will take place in an enormous effect, in an enormous scale. Okay. And we need not bother about this multiplication factor for Zener diode because in Zener diode, the multiplication happens with very, very low value of voltages. V by VBD will be approximately close. By normal PN junction diode, VBD will be close to 100 volt and V value will be very, very small. So in that case, you have to worry about what is the carrier multiplication factor. Okay. So when you can see M value is very, very small until the voltage applied is 90% of your breakdown. When the voltage is more than 90% of breakdown, M value becomes very, very large. So the resulting reverse current will be, it is not simply I naught, it is M into I naught because it is multiplied by the avalanche multiplication factor. So till your breakdown, the current is I naught. After your breakdown, the current is M into I naught, where M is the avalanche carrier multiplication factor. So when you put V equal to Vbd, what happens when V is equal to Vbd? What is the value of M when you put V is equal to Vbd? Can you please say the answer? In this equation, when you put V is equal to Vbd, what is the answer?
Infinity, sir.
Infinity, which means at breakdown, carriers are going to multiply randomly in an infinite manner. So infinite electrons are produced theoretically. But practically, you cannot measure the infinity, right? So practically, they are meaning to say you have a very, very high increase in the carrier density. So the carrier multiplication is going to be very, very high when M is going to be close to VBD. And this will result in the increased current because of avalanche multiplication factor. And this process of breakdown is called as avalanche breakdown. So even if initially the carriers are not able to acquire energy and cross the depletion region, when you apply a very large voltage because of avalanche breakdown, these electrons will possibly cross the depletion region as a group of avalanche of electrons, leading to what is called as a very high reverse saturation current. Okay, so actually in diode, in reverse bias, the current is zero. Theoretically, we say, but if you want to expect a diode to conduct at reverse bias condition also, you have to bias the diode at a breakdown voltage. And that is where the twist is given. If the diode is biased at avalanche breakdown voltage, the diode cannot withstand such a huge amount of voltage and it will actually burn out. But the same thing, I can use the diode in reverse bias voltage also by appropriately doping the diode. Thereby, the breakdown voltage becomes very, very smaller, which will still make the diode on state without even disturbing the physical structure of the diode. So that is what you have to clearly understand in the two types of breakdown, avalanche breakdown and Zener breakdown. Okay. You have a special diode called Zener diode. We will be reading about it in the subsequent chapters. The application of Zener diode and all, we'll be reading it at that point of time. I'll explain you in detail what is a Zener diode.